In this video, we will be looking at something called the kernel trick. And the kernel trick is really part of the SVM machinery. And when people talk about SVM, most of the time they talk about kernel SVM, which relies on the kernel trick. And I felt that it would be useful to have a separate video for you to understand the idea behind the kernel trick. So let's remind us of the problem, okay? So most of the time we want to go away from, we want to still remain in a linear framework, okay? So we know how to use a linear classifier. Even if you think of least squares, then linear models were at the heart of least squares, right? But we saw that maybe we could use a transformation of the feature vector in such a way that it will allow us to somehow get something more interesting in the linear space. By that I mean, if you look at a classification problem, this gray line here might be the boundary between your two classes. And of course, this is not a linear separation between the two classes, right? So this problem is like, how do we design such and resolve for such a non-linear boundary is a difficult one. But what we found is that with the use of the right transformation on your input data, then we'll somehow magically be able to map every single of these points into a point here in such a way that now the class separation is much clearer. And in this case, just finding a hyperplane or just, we have a nice straight line, this to the example. So this is the idea behind transformation. And again, this is something we're going to see in deep neural net, and this is something very important, is how do we transform the original features into something more meaningful? Right, so in the example of least squares application, we were looking at observations of x, and from x we derived a number of other polynomial degrees. So we looked at saying that we transform x, which was just a simple scalar, or where it is on the 1D graph, and then we say, well, if you want to fit a polynomial, then maybe you can transform x into a vector, and the new feature vectors will be something like 1x, x squared, and x cubed, and so on. Okay, and that is simple enough if x is just a scalar, but maybe the type of features you might have might be slightly different. So if you look at a 2D case, so if you have two features to work with, so say example, width and height of a person, so the width would be x1 and height would be x2, then if you want to look at any combinations of these two in a polynomial way, then if you stop at the polynomial of order 2, then you can see that now we have 1, 2, 3, so we have 6, a vector of 6. So we went from 2 features here to now 6 features, which have been just recombining these original features to create more features. And you can keep on going. So, but as you can see, as soon as you here for if you have 3 input features, looking at terms, like combining all these 3 features, you can see already you can start to increase the size quite significantly. And in fact, if you look here, you can see that if we have an input feature of dimension d, sorry, that should have been p really, the transform features are of dimension factorial d plus 1 divided by factorial of n and factorial of d. And this is quite a significant number. And to give you an example of that, let's consider the following problem. So if you have 100 features, okay, so it's not by any means a big problem. And then you're looking at a polynomial of order 5, which again is nothing really massive. The resulting features that we get by looking at possible terms in your in your polynomials, then will be about just short of 100 million values. Okay, so means that you start from 100 features, and then now you're going to expand to 100 million. Okay, so this is not great. Okay, so clearly there is something which is problematic here, and so this is just the size of the feature vectors, of course. Now think if you're doing least square, then you have to look at these matrices, and this matrix will be of size 100 million by 100 million, which would be 10 to the power of 16, which is totally massive, totally impractical, and there's no way you can solve for that. Okay, so we started from a problem which had something very reasonable, 100 features, and we looked at a little trick of trying to expand the number of features we have just by order of using polynomial of 5, which is not, extraordinary. And then we end up with totally impractical solution. So we want to avoid that, and we want to find a way of having to be cursed by this explosion of the size of the number of features. And the kernel trick will do that. Okay, so the kernel trick is a very elegant way of solving just that problem. All right, so what I'm going to do now is I am going to try to go through some of the critical steps of kernel tricks and try to see how reach there. All right, so let's work like this in the context of least squares, but really this is the same. So practically what you have is you have your linear model somewhere that says that your prediction is the scalar product between your feature vector and the weight parameters you have, and you have some error in your model. Okay, so we've seen that many times now, and if you write that in vector notation for all your outcomes, you can write that this is the matrix multiplication between something called design matrix and by your feature vector, and then you have your vector of error here. Now the design matrix is of size, is just, just reminding you of that, is what you're doing here is you're stacking all the observations, and the size of this would be p here because you have p features, and you always have p features, and the number of observations here. All right, so the number of samples you have, the sample size of your problem, so the size of your data set. Okay, so the kernel trick starts with, so let's write that again, kernel trick. So the first step of the kernel trick is to realize that actually W can be rewritten as a linear combination of my feature vectors. Okay, now this is a bit of a strange thing. So what we say is that for most problems, okay, so there is some consideration about the loss functions you're using, as is something which is detailed in the handout. But for most functions, loss functions, you can say that the optimal, sorry, I should have said that here, the optimal solution for your weights will actually turns out to be a linear combination itself of the observations you have. Okay, and this is a bit confusing. Okay, but this actually somehow makes sense because there's clearly a relationship between the x and the w's. Okay, that's all what it says. and in fact, if you want, the w's live in the dual space of this linear equation here. But this is not super important. I'm just putting that as a fact here. You can look at the handout for explanations on why that is. So if you write that into matrix notation, you would realize that the optimal value for W can be written as this time X transpose. Okay, so this is kind of the transpose of the design matrix. So I'll just write it here, what the transpose of the matrix is, which is just now the all the vectors lined up column by column here. Okay, so each column is one of the observations we have. Okay, so this is times alpha. So alpha is your vector of containing the coefficients corresponding to all the observations. Okay, so this is the first fact. Okay, so we know the optimal version for W for a whole range of problems, and not only least square, has to be of this form here. Okay, so that is quite interesting, and but by itself, okay, it doesn't go very far. So what we'll do here now is we're going to plug that into that expression, and we are going to write what we get. So so writing using this matrix form, so we have the vector of all the outcomes, y, is x times w, and let's reparameterize w because we know that it will end up in this form for the optimal version. And we're just going to say now it's x transpose of some alpha that we're trying to figure out what it is. Okay, and we still have this noise term. So what I've done here is we move from this model and linear model, and we reparameterized W, the weights, in this form. We reparameterize it by alpha. Okay, so now the name of the game is to actually find what is the best value for alpha, and it's not about W anymore. Okay, so all right, so what does it mean? Okay, so if you look at this matrix here, why is that interesting? Okay, so we're going to rename that K. This is actually called a kernel matrix, and we just say that Y is K times alpha plus epsilon. But here's the thing. Okay, so if you look at what is this matrix? Okay, so this matrix X times X transpose is, so I'm going to write it explicitly. So this is here we have this stacking of the feature vectors in this way, and now we have this form of the equation, of the design matrix. And so what you're going to end up with is a square matrix whose entries are scalar products between different feature vectors. Okay, so each of the entries of that matrix this should be transpose xn. All right, so each of the entries of that matrix, so that's the scalar number, and that scalar would be xi transpose xj. So there'll be the scalar product between these two feature vectors, or we can write it this way directly. Okay. All right. So we transform this problem here into this new problem, and now we have a system of n equations with n unknowns, so alpha is of dimension. So actually, let's look at the dimensions. Okay, this is the actually interesting part here. So k, so alpha, okay, so alpha is of size, it's n by 1, okay, so this is of size n by 1, and k is of size, so this is of size n by n, okay, so we have all the number of observations n, so each of these entries is the scalar product between the two possible vectors. So really what you end up with is the matrix K, which is of size n by n. Okay, so here's a critical thing. Okay, so in this equation we had x, and x, so let me write that again. So we transformed, okay, so we had, in step, originally we had that, okay, and this is of size, so, all right, so, okay, so this is of size n by p, okay, and w is of size p by 1. And now the new problem, if you want, is we write it this way, and this is of size n by n, okay? So now there is no more p, okay? So this problem is of the size of the number of observations, and there is no relationship anymore to the size of the number of features. So it doesn't matter, like you could have 1,000,000 features or one feature, this will still remain the same dimension, and the complexity of the problem is still the same, okay? So there is no dependence on p, okay? And so that means that this is it's an n by n problem, okay? And this is where it's interesting, because it means that now we have a mechanism to somehow, it's called the kernel trick, to transform your problem into a way that you don't look at the size of the feature vector, but just at the size of your data set. Okay, so all the consideration we had about the fact that it was too hard to invert the matrix because the matrix was huge, well, now the matrices are fine because the matrices are only n by n, and n is the number of observations you have. So it doesn't really matter what we have for p. So let's come back now to the original idea. Okay, so right now we haven't done anything very fancy. We're still working in linear mode. We haven't tried to transform the features in any way, shape, or form. So let's see what happens when we transform x into phi of x. Okay, and I just want to look at what is the impact on this matrix K. So after transformation, so let's call it y, okay, but still a y, we said that we have transformed the matrix, and we're going to call that K prime times alpha prime, okay? No, the notations are not very specific here, it's just me saying that I just add this prime. So let's look at what K prime and alpha prime looks like. So K prime now would be, so still everything applies, but so we had K, 1 and 3 for K would have been, so I said that again for reference. So the transpose between x of I and x of the feature xi, the observation xi and xj. And now in this transform mode, what I have here, it's simply the transform of that feature and the transform of this other feature, okay? So again, maybe I should have started by that. we transform x to a phi of x, sorry, and now if you look at the design matrix, that will be transformed into a new design matrix, which will be made of these transformed vectors, okay? Now the size of this matrix is clearly different. So we still have n on this side, but here we have p prime, and p prime could be much bigger than p, okay? And this was our problem, the fact we had p prime, which was massive. But then when you look at k prime, which is just made using the same technique we had, then we look at k prime, where k prime is still, so if you look at the size of k prime, this is still of size n by n, okay? And we've lost this dependency on the feature vector size. It's still the same. So this problem, okay, so the transform, this is a map problem, and this was the original problem, if you want. So this is kind of like, if you don't do any fancy transformation of your initial features, and this is when you applied your feature transformation. And of course, the values for k in detail are different, okay, because here we apply a mapping, but the size of the problem remains the same, because here we had a n by n matrix, and here we still have an n by n matrix. So it's quite neat, okay? But somehow we still have to compute that, okay? So this is the issue now. We still need to compute that. And this is where the second part of the kernel trick works, okay? So the first part really was realizing that this happens all the time. And the second part now is the following, okay? So we see in our problem, so I'll just say it again, our problem, we have this, and we see that, you know, we need to manipulate this matrix, so we need to know how to compute these kernel metrics. So the entries for that kernel matrix, we said were, so let's use a prime notation I used, okay? Phi of xi transpose phi of xj, so the scalar product between these mapped feature vectors. Now, the thing people realized, and this comes from the theory of reproducible sorry, I'm coughing. This comes from the theory of reproducible Hilbert spaces. So, right, the RHS theory, which is that we could bypass that step, okay? We just say, well, you know what? This is some kind of function of xi and xj, okay? And one example of such a function is the something called, this is called kernel function. So this k prime is a kernel matrix, right? And this little k is a kernel function that takes two arguments, so two vectors, okay, so xi and xj. And an example of such a function would be the exponential kernel, which, you know, I'm going to write it this way, okay? And we say here, okay, we kind of, I'm just taking here, exhibiting a very simple expression for what it could be. So here what I say that this kernel function is going to be basically at maximum value when xi and xj are similar, okay? Because when xi and xj are similar, this difference is null, and the exponential of null is 1. And when the difference is huge, then this value is going to go to 0, okay? So in the theory of reproducible Hilbert spaces, there's theorems that are going to exactly explain what kind of conditions, what kind of functions you can come up with. So I mean, you can't take any kind of function. Obviously, there's some conditions on the function. But if your function has nice enough properties, then you can directly write this kernel function, and which says basically, and here's important stuff. What we say here is that if this function satisfies this expression, then means that there exists a phi such that we can write the function this way. Okay, so we say we can write it this way, and we know that there exists a phi such that phi xi transpose phi xj. Okay, so we know that from this theorem that actually defining this function this way is okay, and there exists a phi transformation mapping on the features that allows you to do that. Now, what is phi? Well, that's the thing. Okay, so you don't need to know what phi is. Phi, actually, in this case, is of infinite dimension. So this is a well-known function, so we know exactly what phi is. But phi is actually of infinite dimensions, so it means like you transform, to make that work, okay, to get to that exponential, nice exponential, you need to transform xi into infinite dimension. Okay, so we say xi is mapped into something called phi of xi, which is a new vector. Okay, and this is of dimension infinity. Okay, so there's a infinite amount of these elements. Okay, and then we say, right, when you do the scalar product between these two guys, then this is going to be actually exactly equal to that quantity here, which is our exponential kernel. Okay? So this is the idea, okay? So you have these kind of two steps going on. You have the first step where, coming back here, where somehow we reparameterize the problem. We went from this equation to this equation here, okay? And that allows us to get rid of P, okay? So we say now we have a state space where, I'm trying to solve for alpha, and that's my weights. My new weights, if you want. But in that space, I don't need to know about P, okay? So that's fine. The second key ingredient is to realize that this K function, which is called this matrix K, which is a kernel, can be generated from a kernel function directly on X, okay? And somehow the phi gets implicitly computed. Okay, so we define directly the kernel function, and then phi, well, we don't need to know exactly what it is. So this is a very powerful technique, and this is kind of an indication of how you do the maths here. What I wanted to mention here briefly the fact you have different types of kernels, okay? But this is the example of decision boundaries for your three data sets are. And I just wanted to highlight the RBF as VM, which is just the kernel technique using the Gaussian kernel. And what you can do here is you can get some kind of nice smoothness going on in the features, okay? So this kernel technique, okay, allows you to define, I would say, what's a similarity metric. So the kernel function we looked at, the exponential, for instance, was actually based on the similarity between two feature vectors. And so it kind of defines, if you want, a neighborhood structure on your space. And so we say elements that are close to each other are very similar in nature, and therefore they should be kind of clustered together. All right, that's it for today.